Hi, welcome to the talk about a heuristic approach to the treedepth decomposition problem for large graphs. My name is Sylwester Swat and it's a joint work with Marta Kasprzak. We'll start with the definition. What is a treedepth decomposition? For a given simple graph G, a treedepth decomposition is a tree built on the same node set as the graph G, where for each edge AB in the graph G, there is an ancestral descendant relation between A and B in the tree T of G. As an example, here's an edge 5, 6 in the graph, and there is an ancestral descendant relationship in the red tree. That's the composition here. And in the tree of decomposition problem, we want to find a tree of decomposition that is the elimination tree with as small height as possible. We'll look for treedepth decomposition for elimination trees from the separator point of view. That is, given a graph, we will look for a separator in the graph, 5, 9, 11 in this case. Then we'll find recursively treedepth decompositions of connected components of graph G after removing found separator. And depending on the separator found, for example 5, 9, 11 or 4, 7 here, we can obtain different decompositions with different heights. Having two or more separators, we would like to evaluate them, that is, decide which one is better. For that, we use given score functions. The smaller value of the score function, the better. And there are two auxiliary score functions, score n and score e, based on values mn of gs and me of gs. Mn of gs is the largest number of nodes in a connected component of graph G after removing separator s from graph, in that case 8 here, and me is the largest number of edges. And having those two values, we can calculate those scores and the final score. That is the linear combination of the two score functions. And the main difficulty usually is to keep track of values mn and me during different algorithms to be able to evaluate all considered separators. Why the formula looks like this? This is just the approximated height of the treedepth decomposition, assuming that in each recursive call for all connected components after removing separators, the values alpha and beta defined here will not change. If they will not change, then the expected height of the treedepth decomposition can be estimated to be just the value. We apply preprocessing before finding separators. The first step in the preprocessing is identifying cactus subgraphs. In the example graph, we have 4 cacti. We remove them from graph and perhaps add some edges to keep the graph structure that we will be able to reconstruct the tree of decomposition afterwards. Here we have to add edge for 7b, that is between nodes that are neighbors of red cactus. After removing cacti, we consider graph induced by all nodes of degree 3. These are marked here by those rectangles. Then we contract them, that is, we add all missing edges between their neighborhoods and remove those nodes from graph. Okay, now we go to finding separators. The first method is articulation point method. It's based on looking for an articulation point in the graph, and it is mainly used for creating treedepth decompositions of cactus graphs found during preprocessing. We use and modify Tyler's algorithm for finding biconnected components. So we run DFS, and during the DFS we calculate low function and keep tracks of sizes, number of nodes and edges in considered subtrees to be able to calculate values me and mn needed to evaluate separators based on our defined scoring functions, score n and score e. And finding score of v can be for every articulation point in the graph can be done in time linear in the number of edges in the graph. In case of a cactus graph, it's also linear in the number of nodes. And we use the method to recursively to find treedepth decomposition of a cactus graph. First best articulation point, then two articulation points, separators in connected components, another step, and we have found the whole treedepth decomposition of considered cactus graph. The whole procedure works in time E log v. The second method is the BFS-based method. Here we consider some initial set of nodes, the purple one here, and we partition all nodes into layers based on their distance from the initial set. Distance 1, distance 2, distance 3, and so on. Then we process all layers in reverse order from the last one, previous one, previous one, previous one, previous one. And for each layer here, we do the following. First, we divide the layer into blocks. Each block contains all nodes that have a neighbor in the same connected component in the graph induced by all earlier considered layers. That is one connected component, so nodes 9, 10, and 11 that have a neighbor in it belong to the same block. Then for each block, we consider its neighbors in the previous layer. We create a bipartite graph with given bipartition and find a minimum vertex cover in that graph. And that minimum vertex cover is our separator. And checking all layers and all bipartite graphs and finding all minimum vertex covers in those bipartite graphs can be done in time E times square root of v. Another method for finding separators is the component expansion method. Here we consider some initial sets of nodes. Here again it is a single node. Then we use some heuristic to expand the set, that is add a node from its neighborhood to the set. We here in the example will use selecting node with tightest connection, that's a node that has largest number of edges incident to the set, to the pink set here. We'll add node 1 as it has one edge to pink set, right? Then we'll add node 8. Now the tightest connection has node 5. We'll add node 5, node 6, followed by 0, 9, 3, 7, and 4. We create our expansion order. And for almost all heuristics used in practice, the expansion order can be created in time E log v, as the information about necessary to create the expansion order can be updated using priority queues. In order to create values mn and me for all separators, that is the boundaries of all sets, of all n sets after adding some vertex to expanded set, we need to store some information about number of nodes and edges in the connected components. We process the expansion order in reverse, just as it was done in the BFS-based separator. Use finding union and some arrays and other structures to gather the information and store it. And in order to create the statistics for our expansion order, we do the same, but processing nodes in normal order, in the order they were added. And knowing those values found by processing nodes in two orders, we can, for each boundary set of expanded set, find statistics and evaluate the separators using score functions. Now we would like to optimize the order, as the order we created has a big flaw. When we added node 1 here, we see that it disjoined our graph. Nodes 0 and 6 were in different connected components than the rest of nodes. But nodes 0, 6, 5, and 8 all have only one node in the expanded set, and we added node 8. Instead, whenever we disjoin the graph by adding some node, we would like to process all nodes from smaller connected components before any other node from larger connected components. That is, instead of adding 8 to the set 1, 2, we would like to consider all nodes from this connect component. That is, we would like to rearrange nodes in already found expansion order so that all nodes from this component precede nodes from larger components. To do that, we create an auxiliary graph, auxiliary tree, and consider our known expansion order from reverse. Consider node 4, node 7, node 3, node 9, node 0. And when you consider node 6, we see that it has a neighbor in already created component 0. So we add 0 to the neighborhood list of 3 created to the neighborhood list of node 6. Then we consider node 5. It has neighbors in components 3 and 4, so we add 3 and 4 to neighborhood list. Then we consider node 8, and we add its neighbors, representatives of the 3 already known connected components, 9, 7, and 5, remembering to add 5, that is the representative of a larger component, after representatives of smaller connected components. Then we add node 1, and here we add node 6, the representative of component of size 2, and node 8 as the representative of component of size 6 here. But we need to notice and remember that we do not add neighbors of node 1, that is, we do not add 5. We add a representative that is a node from considered component that is leftmost in the expansion order. That is why we did not add 5, but 8 that belongs to the same connected component but is leftmost in the expansion order. So we add 6 and 8. Then we add node 2 and add 1 to its neighborhood list. Now we traverse the graph, the tree here, and take the pre-order sequence as a new expansion order. 1, 6, go to 0, back to 8, 9, 7, 5, 3, and 4. And we have a new expansion order. So we can see that all nodes, that is 0 and 6, from smaller connected components preceded node 8, and all other nodes from the smaller connected component here. 2, 1, 6 and 0, so 6 and 0 preceded node 8 in the optimized expansion order. And such an optimization for a given expansion order can be done even faster than finding the order itself. And those expansion orders almost always produce much better separators of much better quality than the expansion orders, than the raw expansion orders without the optimization. Another way of finding separators is using a flow separator creator method. For some two initial sets of nodes, x and y, we find a maximum set of vertices disjoint x-y paths and treat all nodes on those paths as a separator. We have two paths here, we treat all nodes on those paths as a separator, and we need to improve the separator using in particular the GNE minimizer method we'll talk about in a second, because all paths, the union of all paths itself without some minimization usually is a very poor quality separator. The last method for finding separator described here is the flow cutter method by Michael Hau and Ben Strasser. It's an algorithm that works very well for some graph classes. It's a very, in my opinion, very powerful tool for finding balanced graphs. However, there are graph classes, especially graphs that do not admit small balanced separators, for which the algorithm's runtime can be a bit too slow. So we cannot apply the flow cutter method for graphs that seem not to have small balanced separators. Now we go to minimizations, that is improving separators. Knowing a separator, we can and we want to improve it even further. The first method, VC minimizer vertex cover, it is knowing a separator S, we consider its neighborhood in the larger connected component or a connected component for which the treedepth decomposition, if known, is larger. We consider its neighborhood, treat the graph as a bipartite graph, and take the minimum vertex cover that we can quickly find for a bipartite graph, and take the minimum vertex cover as a separator. hoping that it will be better with respect to scoring function than the separator S itself. The second method is BFS minimizer. Now in separator S, we run BFS separator creator method for initial node set S, hoping to achieve, to find some better separator, thus improving the known separator S. Component expansion minimizer, just as BFS minimizer, is based on running component expansion separator creator method described already for initial node set S and hoping to find a better separator somewhere else. And greedy node edge minimizer is based on taking the separator S, creating some auxiliary graph structure where each node in S represents, where each node here represents a node in S, and each blue node here represents a connected component of a graph G minus S. Edges are weighted by the number of edges between given node and given connected component. And now we greedily remove nodes from S, trying to minimize the largest size of a connected component after removing the node. For example, if we remove this node, then those two connected components will be joined, and we want to minimize the largest connected component after removing the node. By keeping those values on priority queues and lazily removing neighbors from the graph structure, we can obtain relatively good complexity for running the minimizer here. Improving separators, another method is based on flow separator creator method. It's called flow minimizer. Now in separator S, we find some set of sources and targets lying in different connected components, far apart from node set S, but containing many nodes, not just single nodes, and running flow separator creator method, hoping to find a better separator. And the other similar is when you have separator S to run not flow minimizer but flow cutter minimizer. It's worth noting that given a relatively good separator S or a separator of some quality, using these methods we can quickly find improvements of separator S, and flow separator creator and flow cutter work much faster when initialized with proper sets of sources and targets than the random ones. Tree merging. If we have a separator found and treated decompositions for connected components found recursively for the graph, then we would like to create a treated decomposition for the whole graph. That is, to do that we sort known treated decompositions by their height, and we'll consider the trees and process the trees in that order. That is, the higher trees will process before the trees with smaller height. Now we consider all nodes, all neighbors of nodes from considered tree, that is here 3 and 2, and we add them as the topmost nodes in the newly created tree of decomposition. Then we process another tree, and 7 is the neighbor of this tree, so it will proceed. It will be after 3 and 2 in the decomposition. When we have found a treated decomposition, we apply some post-processing steps. The first post-processing step method is the block pivot. We select some number of topmost blocks on a root leaf path, that is here, longest root leaf path. We select the 2 blocks, green one, red one, and treat it as a separator. 2, 3, 6, and 7 is a separator. We have treated decompositions induced from already found and already known treated decomposition, and we apply merging. We have 2, 3, 6, 7, 2, 3, 6, 7 separator, and after merging we see that we made some pivots, some rotation in that case, that resulted in reducing the height of our treated decomposition. And this method, block pivots, works very well in practice for almost all graphs, but it usually produces a small improvement in the height. And Yes, and that's how it looks like roughly. When we have the whole graph, we have a separator as here, and a separator in some component, and recursively another separator. That is the structure of our treedepth decomposition. We take here 4 topmost blocks, consider it as a separator. From this separator we select some other separator using block pivot. That resulted in a different topmost separator and very possibly a larger one, but even though that the topmost separator's size could increase, the height of the treedepth decomposition overall did not increase, and hopefully it decreased. The second method based on pivots is the whole set pivot method, and here we again select some number of topmost blocks on a root leaf path. We have a path, we select 2 topmost blocks, then we take a tree, TV, with a root V, that is the topmost node that does not belong to the blocks we considered, and we take U of V, all nodes in our 2 considered blocks here, and D of V, the rest of nodes on the longest path, and the set R is just the set TV after removing D of V. Okay, and now we consider a maximum matching in a bipartite graph induced by edges with one end in set U of V and other end in the set R. That is the matching here between graph with such bipartition. And if the matching M does not saturate the set U of V, then there exists a set H in U of V that is larger than its neighborhood in set R. From Hall theorem we know that, and if so, if such a situation occurs, then we consider the set P minus H, that is the whole path here. From the whole path we remove the set H, then we add the set its neighborhood in R, we treat it as a separator, and we again apply merging for the separator. And this method seems to make almost non-improvements on many graph cases or graph cases that have a relatively, let's call it simple structure, that or on graphs that admit small separator sizes, small balanced separators, but it works very well on graphs that have complex structure or on graphs that seem not to have small balanced separators, such as very dense graphs or random graphs. This method then can sometimes make a very, very significant improvement in the height of the final treedepth decomposition. And briefly about the results. There is a contest parameters, algorithms and computational experiments challenge PACE organized for at least 5 years now, every year, and in 2020 there was a problem, treedepth decomposition. The problem was to find the treedepth decomposition of as small height as possible, and the method extreme solver, in which there are implemented all methods described in this work, won the heuristic track of the 5th parameterized algorithms and computational experiments challenge. Thank you.